Welcome all to the next installment of the webinar series from the American Rock Mechanics ARMA's Underground Storage and Utilization Technical Community. We're pleased to have you join us today for the first of our webinars in the fall lineup. We have an exciting series of webinars planned for you this month and then through the end of October. Our speaker today, Robert Bauer. Bob Bauer has a bachelor's degree in geology from the University of Illinois at Chicago and a master's in engineering geology from the University of Illinois at Urbana-Champaign. He has more than 44 years of experience. Bob is a principal engineering geologist at the Illinois State Geological Survey, where he researches soil and rock behavior associated with coal mine subsidence, landslides, earthquakes, foundations, and CO2 sequestration.
Thank you very much, Richard. This is a presentation on, we have two different injection projects at a Decatur, Illinois CO2 sequestration site, where anthropogenic CO2 from Archer Daniels Midland, who it takes corn, puts it into using a fermenting process, and produces ethanol. A number of colleagues have been working lately on this project. This project's been started injection nine years ago. Charlene Williams-Stroud will be giving a presentation on this in this forum in 2 weeks, primarily on the faulting and some estimates of maximum events associated with that. Paul Jacques has been working on the microseismicity, this entire project. And in recent years, we have folks from NorSAR in Norway working with the waveforms themselves and seeing what additional information can be generated out of them. This project is located in Illinois, in the United States, in the Illinois Basin, which is a spoon-shaped depression. And in this area, we're away from major structural features. Two different projects, the Illinois Basin Decatur projects, has injected 1 million metric tons of supercritical CO2 over a little over a 3-year period, and that wound up being about 900 metric tons per day. That started in 2011 and ceased in 2014. 2.4 years later, after shed-in of that operation, the Illinois Industrial CCUS project started. They're averaging about 1,500 metric tons per day, and they've been going for a little 3.4 years, and we're closing in on 2 metric tons with that operation. They're injecting into the lower part of the Mount Simon sandstone. The thick deposit there, the thickest deposit there in Illinois is a little over 700 meters thick, and we're off to the side a little bit where it's about 500 meters thick. The deposition environment that we're looking at, the lower part of the formation has more of the alluvial fans and braided rivers than the kind of the middle, with some of the encroaching into the kind of the middle part of this diagram here, where we get some small lakes, playas, and the upper part has a little bit more alluvium deposits. The two sites are at the industrial edge of the city of Decatur. Illinois Basin Project has the first injection operation with that has a couple of geophones in it. And really close by is a geophysical monitoring well with 31 geophones in it. And 300 meters north of there is our first verification well, which looks at the pressures. The current project injection is taking place in this array. The same thing, injection well, geophysical monitoring well, and a verification well 2. Verification well 2 was also used during the first operation. This is looking at the kind of general topographic relief of the Precambrian basement and the 4 wells as they're arranged. The Mount Simon, at the bottom of this diagram, where the injection is taking place is 2.1 kilometers underground. We have primary seals, the Eau Claire Formation. We have secondary and tertiary shale formations. We even have more that you consider as seals. The Pennsylvania here is 80% of that is shales. So we have 30 to 35 meters of glacial material sitting on top of that. It was mostly clay materials. This is looking at the Mount Salmon sandstone and the gamma ray and the neutron porosity log with the basement, a lower sandstone here below the Mount Simon and the cap rock. You can see that there's about 3 different sections to this of some similarity. The red here is anything with porosity 10% and greater, and it is approaching, those high peaks there are approaching 30%. We'll look at the base of this on the next slide. So we're just looking at the lower part of the Mount Simon, and you could also see that in the basement, in the rhyolite basement, we have some high porosity, and we have very little. The orange sections here are where coring took place, so we had very little core of the basement, but the microimaging information shows all of this is heavily fractured. One of the surprising things that came up during the injection, which really didn't show up that much during the investigations, there are some really low porosity layers, which are fine grained. They're centimeters to a meter thick, which are forming a baffle to our pressures and possibly controlling where our microseismicity is taking place. And because of the depositional setting, this really can't be a layer that is very continuous throughout this area. This is looking at the all of the 4 boreholes with overlaying their porosities with depth, and you can see the low porosity, this mudstone layer, which we did not see also in the first injection well. This is what some of the cores look like associated with the Mount Simon, and looking at the highest log porosities, 27%, 1 Darcy. All the blue in this micrograph are void spaces, and also the grains are coated with a rind of clay. So that's the only bonding between them, is a very light cementation. There's no silicone bonding between those. Pretty much when you take the cores out, a lot of times they're just kind of falling apart. This is the Argenta, which is that basal sandstone below the Mount Simon, a much lower porosity, but you could see in the micrographs the difference between the Mount Simon and this formation. And the cores of the rhyolite showing, heavily fractured, and we see this in other cores that have been taken in the basements throughout the state. Using the Fullbore Formation Micrographs, you could take a look at the drilling-induced tensile fractures that show up in some of the stiffer layers here. So we're looking at the the poles of the induced fractures and the breakouts, which comes up with a maximum horizontal stress direction of north 68 degrees east. Also in the sonic anisotropy, we're also seeing the same direction. And we see that in other measurements throughout the northern part of our 3/4 of our state with the same type of directions that are using different measuring techniques throughout. We don't have a lot of deep Precambrian measurements, but we consistently see that the high horizontal maximum stress is higher than the minimum, and the minimum is right about at the vertical stress. Looking at the petrophysical Young's modulus, just for the Mount Simon and the Argenta and Precambrian. We'll note that the higher modulus materials will have the higher tectonic forces locked up in them. And you'll note that our first injection operation is down in a low modulus material, and that the higher modulus materials are the Argenta and Precambrian. And using the petrophysical in situ stress estimates, you'll see that when we're up in the stiffer materials, we have that horizontal stress is higher than the vertical loads. This is looking at the first injection operation, the injection borehole here, which had two operating geophones that are clamped to the outside casing of that well. The nearby geophysical monitoring well with many phones in there for looking at using it for the surface seismic work, and our verification well that's about 300 meters north, which has the temperature and pressure readings for this. And for a little over almost a year and a half, there were 5 geophones in that verification well 2 that were down near the level of the injection operation in the first injection well. We had a year and a half of pre-injection microseismic monitoring taking place. A lot of events that are associated with drilling operations and well activity at the site. Also a lot of distant events from our surface coal mines in the southern part of the state. And looking at, pretty much fell out that we had 8 local events in the area with this type of magnitude range and average. When we first started the injection in CCUS1, all of these boxes that you'll see in these diagrams are the Mount Simon. Injection was pretty much using a spinner, looking at what the flow was. About 80% of it was in the lowest injection perforation zone. And whenever we had pressure changes here at pretty much the same level with the pressure monitoring devices about 300 meters north of there, we always saw a change in the pressures here related to changes here within an hour. And that took place throughout the entire three-year operation. You'll see how stratified the pressures are. And as soon as we're above that mudstone, it takes a long time for any pressure changes to take place. But it took 3 months for the carbon dioxide to show up in the ports associated with water chemistry monitoring. And this is what the maximum pressures for injection were up at about 2.7, which is 72% of the frac pressures in that formation at that level. Some of the highest pressures monitored below the mudstone in VW1 were early on in the operation. But for these upper ones above the mudstone, it took 3 years to get up to those pressures. The area also had ground surface deformation monitoring with InSAR that was done by TRE Canada. It first started out with a timeline of a feasibility study. We manufactured 21 artificial reflectors and installed those. It was a short baseline analysis of only 4 months. And we had another whole separate group of folks that were looking at the near surface monitoring and verification and associated with wells and gas in the soil. It was very valuable to have monitoring over more than one season because there were natural variations that seasonally take place, and then could be explained what you're seeing later on during the injection operation. This is the corner reflectors that were assembled at our shop. Here you can see they're painted green. You can see them out throughout the field that we installed them with supports that were over 4 meters deep. After 3 years of looking at the changes that take place, these were the corner markers that were between the injection operation and that well that measures pressures underground. And with 1.2 megapascals, pressure increased down at 2.1 kilometers. If you do some of the back of the envelope calculations, we don't expect to see things at the surface, and really didn't. The operation also, they shot hard surfaces throughout the area. The only place we saw a change was in the coal pile. There were small changes in these pads here, and the material that was used in the pads swelled with water, and you could even see it on site. After 3 years, there was no clear signs of uplift in the vicinity of the CO2 injection, and no significant movement of any of the artificial reflectors. We'll take a look at the development of the microseismicity that occurred. The first events took place within a month after injection started. And soon as we start seeing a clustering of events, we numbered those clusters so that they're in sequential order. The numbers are in sequential order. So after 2 months, started to see a cluster. After 3 months, we started to see a cluster, but that cluster is almost half the distance closer than the first cluster. And we saw cluster 3 development, cluster 4, and I'm just gonna, 2 things to note, that even though seismic activity is moving out farther in clusters, activity is still taking place, and it did this for 3 years. It takes place everywhere throughout. We saw some of the maximum events within 8 months. They are in the Precambrian basement, and those were the maximums. Microseismic activity pretty much took place to the north and west, and it's not simply radiating away from there, but this activity is taking place where you have faults and pre-existing structures that in our early surface seismic work really weren't very clear to see those. Last 4 months, kind of the same thing. Note that the activity is everywhere. It's not just at far reaches or close to the well. We had 18 clusters develop them. Nearly all of those started with activity in the basement. And 90% of all of the microseismic activity is in the basement. Early on, I talked about that the first cluster was farther away than the second cluster. The strike of that feature is pretty much close to 30 degrees. It's the closest one 30 degrees away from the maximum horizontal stress direction. So this should be the highest stressed feature. It says the critically oriented. First motion analysis has indicated right lateral strike motions associated with these directions of faults compared to the instance of stress. U.S. Geological Survey with their surface monitoring showed the same thing, and these clusters or orientations are consistent with our regional stress direction and inducing a critically oriented structures. One of the things we took a look at also was what was going on during the temporary shut-ins and injection for microseismicity. One of the things we wanted to look at was does shut-in increase activity, or we see decreased activity, and so we had the rate of injection tied to each of the events, and normalized events per hour. We saw no difference between the temporary shut-in time periods and injection time periods. And also looking at the median distances and depths, pretty much they're the same. We did see a little lower magnitudes of events during shut-in. And if you're looking at this value here for distance during injection, this is representing only about 5 events that were longer distance away than the 0 injection time period. We looked at this in real detail, also by plotting all of the events for injection versus shut-in. And graphically, you could look at what's going on with injection rates. Pretty much our injection rates running at 100%. When they were shut in, we were down to zero rate within a minute or two. You will note that this activity is starting before the shut-in started, and later, at a much later time, this activity was in the same cluster. Injection rate versus rate of microseismicity. The temporary shut-ins had full stops to them. We found no effects on the rate of microseismicity. We did experiment with stepping the rate down from 100% to 75 to 50 to 25 to 0, and each of those lasting 12 hours. And we saw no effects on the microseismicity. And we also experimented with that and doing the same thing for we're stepping up the rates and saw no effects on the microseismicity. This is a graph looking at depth versus time during the injection and the shut-in that was 2.4 years after the first injection. You'll note the depth, most of these are in the basement, and we are 1,200 feet, 365 meters away from the cap rock. And we could, the lack of activity up here could be a representative of two different things. One that's mudstone barrier, it kept the pressures down, but also our structures, our faulting could be coming out of the basement, could be dying out throughout this really soft sandstone layer. Looking at the microseismic events and the distance away from the wells through time for during injection and shut-in, we're seeing the same activity taking place at all the clusters. This banding is really where that's the distance to the individual clusters. And again, shut-in activity during injection and shut-in were all pretty much throughout the same areas, the same clusters. When the injection started for the second operation, that was moved up to be above the mudstone barrier. This operation also has a thicker perforated section and had higher pressures and volumes going into it. Again, looking at this now with the injection to the second operation, there are pressure and temperature sensors at each now 3 different locations with this operation. And we looked at this before. So during this first operation and looking at these values, these were the maximums. And then now looking at up to June of this year, what the maximum pressures were. And these sensors were in place for a month into the second operation, and then we had new ones switched out. But you will note that above the mudstone, the pressures exceeded the previous induced pressures. And this took place, they were exceeded within a month. So this lack of activity doesn't seem to be related to the pressures, but may be related to the lack of structures up in that area. So now looking at the first injection, the microseismicity during injection, shut in, and this is the level of injection for the CCS2, but its activity is still down in the same areas as before. Looking at the averages over time for the activity, we're looking at 1 event per 2 days for this. But if we look at after 4 months, when this was kind of ramping down a little bit, we're looking at the same activity as we are with the second injection right now. And the second injection here is the rate is 1.7 times higher, and the pressures are 3.2 times higher pressures. And the activity, again, with first injection shut in and current injection. They're all happening at the same clusters. Same thing with the distance for the events. Again, tied to those pre-existing structures, and looking at injection shut-in and current injection operation, the location with the depths through and the distance away from them. You will note two things or three things. They're all at the same kind of the same activities taking place, but also the distance out to in the sedimentary layers. It's a similar for both during injection and shut-in, and in a basement, same thing for all of these three. We're seeing the same distances. This is what a traffic light system for the permit looks like when a corporation and its lawyers get involved. I'm not going to go through the details on this, but this was in the permit. There was a traffic light system set up primarily with looking at some activities that would take place if you had 1.5 magnitude or twos or things were being felt. But this wound up being five different operating states associated with that. Kind of the summary that we're seeing with this is the microseismic activity is in distinct clusters along previously undetected pre-existing critically stress-oriented faults and fractures. Nearly all the cluster activity first started in the basement. The first clusters seem to be controlled by the critically oriented direction that was spot on for the maximum stresses. And then we had a systematically migrating seismicity front away from the injection well, which kind of indicates that these things are pressure controlled more than poroelastic. Because of the orientation and the in situ stresses producing right lateral fault motions, and the range of microseismicity, 95% of these are below magnitude 0, and 90% of the activity is in our Precambrian basin. We had no bursts of microseismic activity related to startup or shut-in during the operations. No increase in seismicity rate in the near field with the shut-ins. They were scattered throughout all of the clusters. The largest maximum events are in the basement, not the sedimentary layers, and they're occurring in where we should have the higher in situ stresses locked up. The microseismic locations during first injection shut-in and second injection operation are occurring in the same locations as of the pre-existing structures. The distance from the injection wells for injection, the distance for the microseismic activity for the injection wells and shut-in is similar in the sedimentary and the distances and also in the basements. The microseismic activity is the greatest distance from the injection wells in the basement. Question mark, is this controlled by the stratigraphic height of the structures and not just necessarily the pressures. And the acknowledgements of our funding sources, and let's take a look to see what questions that we have associated with, do we have any questions in the chat room?
Yes, there is one question, I think, in the chat.
The question is, why are most of the microseismic events are in the Precambrian basement?
Why are they in the basement?
Yes.
They're occurring along pre-existing structures. We feel that the faulting in the area is associated with motions that took place in the basement, and we don't believe that the activity is not higher up in the sandstones. If faulting started in the basement, trying to make its way up into the soft sandstones, the energy is going to dissipate and not carry through that sandstone layers to any higher. So I mean that's our interpretation. And they're occurring along where where we have pre-existing structures that are critically oriented with our stresses. Basement, okay, very interesting. There's no relation between the injection rate and the microseismic event rate. That controls what controls the rate in the field. What we see occurring is that we probably have to get to a certain level of pressure, a pressure front that intersects the pre-existing structures, and we see that area light up. So it's everything appears to be more pore pressure controlled, and the activity that associated with these pre-existing structures. We don't have a cloud of activity around that well. You saw reverse fault in the stress gradient plot, but later strike slip stress later. Well, there's two things. One, you have a stress regime, and two, you could have a fault, and under different regimes, you could have different fault slippage on pre-existing structures. A fault regime doesn't mean that you're fracturing new rock under that regime. So if you have a high horizontal stress, say we have a high horizontal east-west stress, it's really high, and we have a vertical fault. Turn that orientation within, to 30 degrees from that direction, and you have the highest stress on that. Okay. Now take a flat-lying fault plane and turn it so it's 30 degrees to that high horizontal stress, and you could get that fault plane to move. So we're looking at the high horizontal stresses that we have, its direction, and the critically oriented pre-existing structures are reacting to that. And our pre-existing structures are oriented vertically in this area, because we do have pretty much most of our natural earthquakes that take place are in the basement. They wind up being strike slip, but we had one down in extreme southern Illinois that was reversed, and we did have a seismic profile line across there, and it's a nearly flat lying horizontal feature that was within 30 degrees of horizontal. Increase. Have you noticed any increase in microseismic as the pressure increases by 2%? No, we haven't seen the microseismic activity increase since the shut-in associated with the second injection operation. But the pressures below that mudstone layer they're only up to about half of what that area saw before. So we're hoping to see higher. We'll see if we get the higher pressures and those kick off some of the microseismicity. Does a 3D model simulation exist for this formation? There are some folks working on some of the pressure models. We do have some models that are mostly from the basement up for pore porosity, permeability, modulus. So those things have been going into mechanical earth models, but we have very little of that in the basement where most of the activity is taking place. I'm still working on folks working on a full 3D fluid flow coupled reservoir and tying it to microseismicity. But again, we have really poor coverage for the basement, a little bit just in the upper part of the basement. We never expected a seal on the basement. All of our findings in different borings in the Precambrian basement finds it to be highly fractured. So we really didn't expect that to be a seal. So we're getting pressure far out distance in the basement through the many fractures that exist. Question, I suspect the injected CO2 goes in the basement. The top CO is actually pretty good. Well, the pressures are going into the basement. How much CO2? Looking at 4D images, the CO2 at a certain higher concentration rate hasn't gone very far to the north. We also believe that we have a fault between pretty close to the injection well, that first injection well, and between it and that first monitoring well. So we do have pressures increasing probably throughout the basement. How far the CO2 is going, we don't know. The question was, do we find out the distribution of injected CO2 in this test? Again, we had the 4D analysis that was done, and that's been published in several different places associated with the first injection. New question about temperature. The temperature of the reservoir and the temperature of the injected material, they were within like 5 degrees of each other. So there is no big thermal effect.
This concludes our webinar, and thank you very much. Thank you, Bob. And
Thank you.